Hi, this is the Earth Science Classroom. Welcome back to the Plate Tectonics series, and this video is looking at Flexural, Isostasy, and Isostatic Rebound. It's kind of like a follow-on video to Isostasy and Buoyancy, which was done previously. So it's like a part 2 type video. And we're going to look at first what is Flexural in regards to Isostasy. We're going to give examples of this and how the lithosphere is going to be more elastic than the crust and how it gives when there is a load applied. And then third, we're going to look at isostatic rebound. All right, when there's a mass removed, in particular, looking at glaciers, okay, as a good example. So, guys, join me now for this video. All right, so first, let's look at flexural isostasy. Like, what is it? What it is. All right, so pretty much the crust, which is the load, right, is the mass or the weight, which includes gravity. The weight applied, which is going to obviously be referred to as the topography. So whether you have an ocean, a mountain, some sort of like accumulation of ice sheets, but the crust is going to differ in the size. And it sits on the, or attached to the lithosphere. Now, lithosphere is a lot more elastic than the crust. So there is some sort of bending when a load is applied. So there's going to be some bending with a mountain range, or bending with accumulation of sediment, accretion of wedge maybe, but it's a large scale mass. Okay, and the lithosphere is going to bend. Now it bends based on the strength of the lithosphere, and that could be the thickness and also composition. Okay, now there's two types. There is local versus regional flexure. Now, local obviously is small size and regional is large based on the definitions. And local is in relation to Airy's theory of isostasy back in 1854 when they surveyed part of India with the Himalayan mountains, and there was definitely that route was there, or he discussed it as a lava area underneath the mountain that equated for the change in plumb line value, the error that was found. However, regional flexure is going to be where the lithosphere compensates for the larger mass by spreading out. Obviously, there's subsidence, there's movement down, but the spreading out of the mass over a large area. Now, usually it's about 100 kilometers up to around 300 kilometers. That's based on different areas. Whether it's a mountain range or a local or an ice sheet, there's different sizes. Therefore, there's a range in how wide that spread can happen, that flexing can happen within the lithosphere. All right. So I like to visualize these concepts to the students and let them see what's going on in like a step-by-step process. So this is like the step one, right? Where you have the addition of an ice sheet. Maybe it's a glacial period in the Earth's history, or there's a mountain range as an origin or orogenic development going on with the Himalayan, the Alps, the Rockies. And you have this load that is added on to the crust, which sits onto the elastic lithosphere. So elastic means that there is some sort of bending, there is a degree of strength that allows it to bend and hold on to the load. So as the load is applied, there's going to be some, obviously, extra mass and weight. And what's going to happen is lithosphere is going to take that load, that weight, And obviously, there's going to be some subsidence, right? Some movement down, some dropping down. So it would look like this. You have this kind of like elongated, stretched out there, and have the load like this. So you'd have this depression created, this large depression, this subsidence within the elastic, EL, elastic lithosphere, where there's obviously movement down and movement to the side to spread out. So it wouldn't just be like this, where like that. There's more of a gradual, more curvature, gradual essence to this lithosphere rather than just a straight down. This would be like airy with a local things, local flexural. So this is more regional, where you have the spreading out, where it could be, the width could be 100 kilometers to 300 kilometers, and really, this kind of plastic mantle or asinosphere also has a higher density, also would push back with the force of buoyancy from Archimedes and create this kind of situation where it's stretching and pushing out the energy and the mass on the sides. So once we have this flexure kind of characteristic within the elastic lithosphere, and obviously we have this asinosphere layer, which is our plastic layer, which is obviously higher density. Once you remove the load that caused the flexure in the first place, whether it be an ice sheet or mountain, let's just take ice sheets. So it's easy to understand, the removal of an ice sheet through changing temperatures, a warming period, an interglacial period caused by Milankovitch cycles and the changes. So you have this melted and moved further north or south, depends on the hemisphere. The ice sheet is gone. So because it has elastic deformation and elastic characteristics, you're going to have a very slow rebound effect, just like in earthquakes with elastic rebound theory. You have this slower rebound where the area of flexure is going to push up because the mass is gone, the weight has been removed, so there's less weight sitting on top of the lithosphere. So what's going to happen is the force of buoyancy is going to readjust and create a new equilibrium and push back up, and there'll be a slow movement of the lithosphere and crust back up to somewhat of an original position prior to that load being added in the first place, so before the glaciers happened. So this is called isostatic rebound, and when it's in relation to glaciers, it's called GIA, which is glacial isostatic adjustment. And this kind of occurs in mostly northern hemisphere areas, such as Canada, okay, over the Hudson Bay. You have obviously Greenland, which still has majority of its ice sheets, but currently they are diminishing. Antarctic, again, but this is more like in theory, if it was to be removed fully, the rebound by the continent, the landmass, and obviously Scandinavia. Norway, Finland, Sweden, they've seen slow rebounds over the course of thousands of years, shown by satellites and seismic readings and remote sensing. We can see there is slow rebound both in Canada and Scandinavia because of the removal of the ice sheets, 18 to 12,000 years ago. And you see the lithosphere kind of adjusting to this new weight or lack of weight on top. So there's an adjustment there. So you can go into more details, like a case study of both Scandinavia and Canada, which is awesome. And then obviously, if worse comes to worse and all the ice sheets melt both in Antarctica and Greenland, you can do a little conceptual idea of what would happen then with land masses besides the sea level as well, which would drastically increase. So this is kind of like, again, geophysics, looking at the adaptation to load on the elastic lithosphere and tying in isostasy and tying in different case studies to this topic. All right, hope you guys enjoyed the video. If you're new to the video, please let me just subscribe and leave a message, and I'll see you in the next video.